differential equations. So before we start, we're going to have a quick recap on our integration basics. So again, relying heavily on page 26 in our maths tables for this chapter. So if we look at the first rule of integration, it's our general rule, which is this one up here. And that states then if we integrate any x term to the power of n, then when we integrate, we add 1 to the power and divide by the power. We also will have to put in plus c if we have no limits. So for example, if we integrate 5x squared plus x plus 2 with respect to x, then we would get 5x cubed over 3 plus x squared over 2 plus 2x plus c. Second one is natural log, which is here on the maths tables. And you can see there on page 26 that if we integrate 1 over x with respect to x, we get the natural log of x plus c. However, most of the time we'll get something like this, where it's 1 over a function in terms of x, where that function is linear, and therefore when we integrate, it will be natural log of that function divided by the derivative of that function plus c. Let me say f of x is linear. So for example, if we have 1 over 2x plus 1 and we're integrating with respect to x, then it would be natural log of 2x plus 1 divided by the derivative of 2x plus 1. So if I differentiate 2x plus 1, I get 2, and then that's plus c. And of course, that can also be written as a half natural log of 2x plus 1 plus c. So the third one is exponential. So the easiest one to integrate. So if we integrate e to the x dx, we can see here on page 26 in our maths tables that we get e to the x plus c. But of course that would just be too easy. So we normally get something where it's e to a power, where the power is a function in x. And therefore when we integrate, it will be e to that power divided by the derivative of that power plus c. So again, if we look at an example, we could be asked to integrate e to the 2x dx, which would be e to the 2x divided by the derivative of the power. So the derivative of 2x is 2 plus c, or that could be written as half e to the 2x plus c. So our fourth one is trig. So if we have cos or sine, or we have sine inverse and tan inverse. These are the main ones that we're interested in for applied maths. Then if we integrate cos x dx with respect to x, we can see there in the tables we get sine x plus c. But of course we could get something where it's cos of a function, which means when we integrate it would be sine of that function divided by the derivative of that function plus c. And the same can be said for sine. If we integrate sine x dx, we get minus cos x plus c. Or if we integrate sine of a function with respect to x, we get minus cos of that function divided by the derivative of that function plus c. So for example, if we were to integrate cos 6x dx, we would get sine 6x divided by the derivative of 6x, which is 6, plus c. And again, that could be written as 1/6 sine 6x. And if we had sine 3x dx and we wanted to integrate, that would be minus cos 3x divided by the derivative of 3x, which is 3, plus c. And again, that could be written as minus 1/3 times cos 3x plus c. So if we're looking at inverse trig, I'm going to the next page actually. These are always the ones where you have to recognize the function. So if we have 1 over the square root of something squared minus something squared, then we should spot that as sine inverse of x over a. But often we'll get something like 1 over the square root of a squared minus a function in x squared dx. And again, we'd have to write that as something squared. Then when we integrate, it would be 1 over that function differentiated times sine inverse of f of x over a plus c. And I should say plus c there as well. And if we had one over a squared plus x squared dx, then that would be 1 over a tan inverse of x over a plus c. Or if we had 1 over something squared, something in terms of x squared dx, then that would be 1 over the function differentiated times 1 over a times tan inverse of the function over a plus c. Okay, so if we have a look at an example, if we have to integrate 1 over the square root of 100 minus x squared dx, then we could write that as 1 over the square root of 10 squared minus x squared dx. So this would be a, this would be x in our answer. Then that would be sine inverse. X is just x and a is 10, and then plus c. And if we look at a tan inverse example, could be asked to integrate dx over x squared plus 9. So we'd have to recognize that that is the same as saying dx over 3 squared plus x squared. So 3 would be our a, x is just x. And therefore, if I integrate that, that would be 1 over 3 tan inverse of x over 3 plus c. Okay, so we're going to look at type 1, which is first order differential equations. So in these questions, what we're going to be doing is basically getting y on the left and x on the right, and then we're going to be integrating one side with respect to y and the other side with respect to x. So we're going to be finding a general solution, or the equation for y. So the first example here is from page 210 in your books, where we're asked to find a function y is equal to f of x such that dy dx is equal to 2y. And we're also told that y is equal to 1 when x is equal to 0. So what we do is we write down dy dx is equal to 2y, and we're going to bring all the y terms to the left and all the x terms to the right. So in other words, we'll have 1 over 2y dy is equal to dx. Or we could leave the 2 on the right hand side and have it as 1 over y dy is equal to 2 dx. So either way is fine, but often keeping the constant on the right is actually easier. So now what we're going to do is we're going to integrate both sides. So we have to set up our integrand. So we have 1 over y dy is equal to 2 dx. And we're going to sub in our limits. So what are our limits? Well, we say at the start and at the end. So we're told at the start, y is equal to 1 when x is equal to 0. And at the end, y will just be y and x will be x because we're asked to find the function y equals f of x. So we're not given anything at the end, so it's going to be in terms of y and x. So we have our start limits are the lower limits. So these are my lower limits. And the end are always the upper limits. So therefore we'll have y, x, and we'll have 1 and 0. So if I integrate 1 over y, we know from our basics there that that's going to be natural log. Or if we look on page 26 in our maths tables, we can see 1 over x is natural log. So therefore that's going to be natural log of y within the limits of y and 1. And if I integrate 2 with respect to x, then that's going to be 2x. And subbing in my limits of x and 0. Now we don't have to put in plus c here because obviously we have limits. So this is a definite integral. So natural log of y minus natural log of 1. So it's always the upper limits minus the lower limits. 2x minus 2 times 0. So natural log of 1 is 0. So that means we have natural log of y is equal to 2x. And now we have to remember our log rules. Or else we go to page 21 in our maths tables. And if we look at the top right hand corner, we're changing from logs into indices. Okay. So when it's natural log, we have to remember that natural log of y is the same as saying log y to the base e. So therefore, if I'm going from logs back to indices, then that's going to be y is equal to e to the power of 2x. So that's y in terms of a function in terms of x. Okay, so let's look at a second example, so 12.8. So again, we have dy dx is equal to xy. So we want to get x and y on separate sides. So therefore, if I divide both sides by y, I get 1 over y dy is equal to x dx. So again, I'm going to be integrating. And I need to look at my limits. So my limits at the start is going to be y is equal to 3 when x is equal to 0. And at the end, we're finding a function in terms of y and x. Okay, so if I integrate 1 over y, same as the last example, it's going to be natural log of y. Sorry, I forgot to put in the limits there. 3, 0. So that's natural log of y within the limits of y and 3 is equal to add 1 to the power and divide by the power, so x squared over 2. Sub in my limits, so natural log of y minus natural log of 3. X squared over 2 minus 0 squared over 2. So this time I have to remember my log rules here because I don't have natural log of 1 in this example, so I have to apply my log rules. So if I'm subtracting my logs, I will then divide. So that's going to be natural log of y over 3 is equal to x squared over 2. But of course, natural log of y over 3 can be written as log y over 3 to the base e, which means then that that can be y over 3 is equal to e to the power of x squared over 2. And then just multiply both sides across by 3, gives me y is equal to 3 e to the power of x squared over 2. Okay, so one more example. So we'll look at example 12.9. So we're given dy dx is equal to x y squared plus 4x. So this time we're going to have to take out x as being common before we can separate our dy and our dx. So that leaves me with y squared plus 4. So if I divide both sides across by y squared plus 4, I get 1 over 4 plus y squared dy is equal to x dx. And now if I set it up to integrate, we'll have 1 over 4, which I can see is going to be something squared plus something squared is equal to x dx. And again, if I look at what are my start and my end limits, so this time we're actually given end limits. So at the start, we have given that y is equal to 2 when x is equal to 1. Find the value of y when x is equal to 2. Okay, so that means my start limits are my lower limits and my end limits are my upper limits. So when you're finding the value of y, we just sub in y for the upper limit, but this time we have an upper limit for x, it's 2. So again, we should spot that we have 1 over something squared plus something squared, which is of course tan inverse. So therefore that's going to be 1 over a. So I can see a is 2. So that's 1 over 2 times tan inverse y over 2. And that's within the limits of y and 2. And then that's equal to x squared over 2 within the limits of 2 and 1. Okay, so subbing in our values then. So we have a half tan inverse of y over 2 minus a half tan inverse of 2 over 2 is equal to 2 squared over 2 minus 1 squared over 2. So therefore that's a half tan inverse of y over 2 minus a half tan inverse of 1 is equal to 2 squared, which is 4 divided by 2, which is 2 minus a half. Okay, so that's a half tan inverse of y over 2, and then that's minus a half and tan inverse of 1. So it'll always be in radians here, so just note that. So when we're integrating, it's always radians. So therefore we have a half times pi over 4, and then 2 minus a half is 3 over 2. So I'm going to multiply across by 2 here just to eliminate those fractions. And therefore that's tan inverse of y over 2 is equal to pi over 4 plus 3 over 2. Or sorry, plus 3 I should say. And then I have tan inverse of y over 2. So if I get the reverse of that, well then that means y over 2 is equal to tan of pi over 4 plus 3. And therefore y is equal to 2 tan pi over 4 plus 3. And it said correct to 1 decimal place, which is equal to 1.5. making sure your calculator, of course, is in radians. Okay, so this used to be a guaranteed A question, but since the maths course changed a few years back in 2012, integration has been revised as such, and we don't do substitution anymore. So there's a few questions on the old course in applied maths from prior to project maths, so prior to 2012, which won't be relevant to us anymore. So you're going to be doing as many exam questions from 2019 all the way back, looking at question 10A, and you'll see that then on your worksheet. So I'll have marked a few that aren't relevant anymore.